Our next speaker is Pratik Jain. Pratik heads the foundations and optimizations team at Google AI. And Pratik has been working in theory of machine learning, non-convex optimization, alternating minimization, theory of deep learning. So he's very well regarded in all of these areas. Today he'll talk about reverse experience replay, effective way to learn with dependent data.
All right. Thanks, Amit, for the wonderful introduction, and thank you everyone for attending the talk. Thanks to the organizers for this wonderful workshop. For this, I prompted GPT to produce this nice poem, where I would definitely want to sort of thank my collaborators Dheeraj and Praneeth, who have been main driver behind this project. But there are some other wonderful collaborators also who have contributed to this project. The goal of this work is to learn with dependent data. So before going into what we mean by that, let's first set up the problem, right? So suppose we want to do our standard machine learning, that is supervised in the supervised setting. That is, we want to minimize some loss function of a network or a model that is parameterized by this parameter W. And this loss function is measuring fidelity for a given data point X. And we assume that these data point X are sampled IID from some fixed distribution pi. Right. So here, stochastic gradient descent and algorithms similar to stochastic gradient descent are workhorse of such stochastic optimization. What they do is at each step, they will sample one of the data points uniformly at random from this distribution, take the existing parameter WT, compute the gradient, and subtract it from the current parameter with some learning rate or step size, and this works well, right? And the reason this works well is that this is essentially in expectation just gradient descent, which means that let's say if the function is strongly convex, then we will converge pretty close to the optimal solution, at least in the function's value, up to an error of 1 by capital T, where capital T is the number of points that we have seen so far, right? And this is known to be information theoretic in this setting. People have studied this optimization in variety of other settings. So for example, when the function is not strongly convex, but it is smooth, or in some cases, people have also studied this kind of problem when the function is non-convex, when the function has some kind of min-max form. So the problem is very well studied in general, right? So this is a story for standard supervised learning. But in ML, there are various other paradigms which are quite interesting as well. So for example, you might have some kind of time series forecasting or reinforcement learning, where this nice assumption that all my data points are sampled IID from a fixed distribution might not hold. So let's look at time series prediction. So suppose this is some kind of, let's say, price graph of your stock. Say stocks of Google, right? So you might, typically these time series are modeled with autoregressive models. That is, you will look at, let's say, the stock price value of 2 days back, yesterday, and then you will try to predict what is the price value today, right? And like once you observe today's price value, you can say that, okay, this is my learning tuple. I will take xt minus 2, xt minus 1, and xt. Xt is my target, the value that I want to predict, and xt minus 2 and xt minus 1 are my inputs. And I want to come up with a network that is able to predict xt. Now, the next point that you will provide to your model to learn will be yesterday's value, today's value, and you will try to predict what is the value going to be tomorrow. And then once you observe tomorrow's value, you will again feed it into your system to update your parameters, right? So now these two tuples of points you can see are dependent on each other. So you cannot directly apply your standard SGD kind of analysis. Even more interesting problem setting happens in reinforcement learning. So in reinforcement learning, typically you have some kind of system. Let's say consider a board game. You have some kind of current state of the board game. You as an agent take some action. So you make some move on the board. And for that, you will maybe receive some reward or you will go closer to your goal, right? So the tuple from which you would want to learn is some state, some action that you took, and some reward you obtained, right? Now, once you have obtained that reward, you will then you will go into next state, right? So typically based on the current state and the action that you've taken, you will go to the next state of the board. And that transition might be deterministic. In some cases, it might be probabilistic, but nonetheless, the transition will be dependent on the current state and the current action, right? And then in the next state, you will again take a new action to go to get some reward. And you will again try to learn from this tuple. And here again, you can see that there is intrinsic dependency between these sequence of points that you're getting. So this is what we are calling learning with dependent data. In general, like, you can model these dependencies between data points in a variety of ways. Let's consider very, very simple setting, which is quite applicable in practice also, which is that of Markovian chain. That is, we are assuming that these data points are sampled from some Markov chain. Right? And the goal is to design streaming SGD style algorithms for this Markovian data. Okay. All right, so let's define the problem formally. Suppose I have a bunch of points x1 to xt coming from a Markov chain with some stationary distribution pi, and our goal is to optimize the loss function under this stationary distribution. Now, if you do standard SGD, that is at th step, you sample some data point xt and apply the gradient descent step to it, the standard SGD analysis does not apply anymore. And the reason is because xt itself is dependent on wt minus 1. So the expected value does not match the true gradient. Right? So SGD will be biased, and in general, it might not converge to the optimal solution. You can try to get away from this problem by saying that, okay, I will do very, very small steps. But in that case, your convergence is quite suboptimal, so it's not desirable. And in practice, people generally don't do that. Right? So how do we solve this problem? So there is one very simple idea, which is that because we are sampling from, say, some Markov chain, we are assuming that Markov chain has some finite mixing time. So mixing time, what it essentially means is that if you consider points which are the mixing time tau mix apart, then they are roughly independent of each other. So now what you can do is you can come up with a very simple baseline called stochastic gradient descent with data drop, where you take, say, point x0, you drop the next tau mix points, you take the next point, you do SGD with it. Because this x tau mix is almost independent of x0, you can apply your standard SGD analysis and get your good sort of properties. You can again do the same with the x2 tau mix, etc. Right? So that's great. We can apply our existing framework, existing analysis as it is. But note that here we are dropping most of our points, like a big fraction of our points are completely dropped, which is not desirable in practice. And that would also reflect in our convergence rate. That is, our convergence rate will have terms like tau mix by capital T, which is much worse compared to, say, 1 by T rate that we get for IID setting. Yeah.
Are you actually dropping the data points, or are you using them but not counting them in the analysis?
So the standard SGD data drop completely drops it, like it doesn't use them at all. But you are pointing to a correct direction, like we will want to use them somehow, and that's what this talk will be about. Yeah.
Shift everything by 1 by 2, you can just use it as
but the dependencies will still be there, right? Like just shifting cannot help. You need to do something more on top of it. And I'll give you examples of what kind of things we can do. Any other questions, by the way? Feel free to stop any. Okay, great. All right, and in fact, like, in general setting, this is the best we know theoretically also. That is, like, there is this nice paper by John Ducci, Alek Agarwal, and collaborators, where they come up with this algorithm, and what we show is that, unfortunately, this is a lower bound also. That is, in general, like for arbitrary Markov chains, even for linear regression problems, your best convergence rate that you can hope for is tau mix by capital T. And actually, this bound is not even dependent on just, say, applying SGD algorithm. This is an information theoretic bound. So you cannot hope to do better than this in general, right? So this makes us sad, and GPT thankfully has written a poem about it. But it says that we must keep on going. We must push forward. So what do? Well, like any sort of theoretician, what they're solved, we will put some assumptions on the problem and try to make it easy. But we'll try to make sure that the assumptions are reasonable, right? So one type of assumption that we found which works well is that suppose we put some kind of assume some kind of realizability. That is, suppose we are looking at the linear regression problem. That is, we have some linear model or linear function that we apply to x, which is given by inner product of w and x. The goal is to find w, and the target is to find optimize against this target variable y. So here, suppose we assume that there exists some w star, so that y is given by inner product of w star comma x plus epsilon, where epsilon is a Markov, comes from some Markov chain, let's say, but expected value of epsilon is, let's say, 0. So we are putting this realizability assumption that there is indeed a w star, which is an optimal solution with some noise epsilon, which is 0 mean. So under this situation, we can show that there will be some, information theoretically, we are at least safe. That is, there exists some algorithm which will achieve 1 by t rate. Now the question is that can we come up with some streaming SGD style algorithms to achieve this rate? And we also want those algorithms to be practical. Like, you don't want it to be sort of things that we cannot really use in practice. So for this, because this problem, as I mentioned earlier, appears very regularly in things like time series analysis, and particularly in reinforcement learning. So people have come up with a bunch of techniques to solve them, although they didn't really analyze them very rigorously. But one very sort of practical heuristic that is being used is called experience replay. So the idea is very simple, as it was mentioned. So what we do is we take our data points and divide them into some buffers. These buffers can be overlapping also. And now what we do is, in each buffer, we will process data points in some order. So they don't need, and we don't, so SGD generally will process all the points in forward order. That is, it will first process this point, then this point, then this point, then this point, then this point, and so on. But in our buffer, maybe we are allowed to process data points in different order. So for example, there was this a technique called uniform experience replay proposed in 1992, where you take each buffer and you sample points uniformly at random from this buffer and process them. Right. Another idea is, which is actually quite popular in recent past and was also used in these techniques called DQN, which you might know from AlphaGo. So those techniques typically use prioritized experience replay. So there the idea is that we look in the buffer what is the loss value that a data point got, and we will prioritize those data points, right? Unfortunately, so far, we don't know of any analysis under reasonable settings for these two techniques. And as we'll show you, I'll try to show you a little later, that actually these techniques might be very unstable and might not give you very good results in general. Recently, in 2019, Rotino proposed this technique of reverse experience replay. It was sort of a concurrent work, so we also came with this similar technique around the same time, which processes data points in reverse order in a buffer. So you take a buffer, and rather than sampling from the buffer randomly or in some kind of forward order, we are taking the last point, first processing it from our SGD algorithm and going backwards, right? So, so this is basically our reverse experience replay method that we use, which is that take each buffer. All the buffers are non-overlapping, and in fact, we have some kind of gap between these buffers. This gap is there to ensure that individual buffers are independent of each other. So if we have a gap of, let's say, tau mix, then because of mixing time gap, these buffers at least will be independent of each other. Within buffer, there are obviously dependencies that we'll need to worry about, right? And within a buffer, now we are going in reverse order. So that's it. That's a simple idea that we would want to use, and try to show that this algorithm really works in theory also. Okay, so let's look at a very precise problem and see how this algorithm will work. So let's consider the problem of learning linear dynamical systems. So what the problem is that this can be thought of as a standard autoregressive model or VAR model used in time series analysis. That is, we have some data point xt. We generate next data point xt plus 1 by applying a linear transformation A star to it plus some zero mean noise. Right, and the goal is, given this single trajectory of x1, x2, so on, estimate A star. This you can write as this simple optimization problem that is given xt plus 1 and xt, you want to find an A that minimize the L2 norm square distance between them. And this we can write like, it's empirical version like this, empirical risk minimization version like this. Now, if you apply stochastic gradient descent, the stochastic gradient descent will have this gradient term, and clearly because at minus 1 is dependent on xt, and xt is dependent on xt plus 1, or other way around, xt plus 1 is dependent on xt. Because of that, you cannot really apply, like you can apply stochastic gradient descent, but it will have some bias and it might not converge to the optimal solution. How does the SGD RER works here? The idea is very simple. As I mentioned, you take one buffer, process the last point in the buffer. That is, I will take xb minus 1 comma xb pair, which is the last point, and I'll apply gradient to it for my first iterate A0. Then for my next iterate A1, I will take the next point in the buffer, which is xb minus 1, xb minus 2, and again apply this gradient descent, and so on. Once this buffer finishes, I will leave the next tau mix samples completely, and I will start processing the buffer, the second buffer from here, one by one, right? So this is the simple algorithm. And what we observe is that the simple algorithm, when we apply it to this problem of learning linear dynamic system, gives us nearly optimal solution, right? So what does this theorem say? This theorem says that after t steps, that is after seeing t samples, we will be able to recover this matrix A hat, which is close to matrix A star in L2 norm sense or operator norm sense, up to this much of error. So this error has this term of D, which is the dimensional T. Sigma square is the variance of this noise epsilon T. In the denominator, there is a smallest eigenvalue term of the Gramian, and we have the number of samples T. So this is sort of the standard information theoretical optimal rate that you can hope for this problem, right? Note that there is absolutely no dependence on the mixing time here. So this is what you would hope for from the sort of the optimal rate that you would hope for. Okay. And we can extend it, this technique, to nonlinear dynamical system, etc. Yeah.
It must be for capital T, which is much bigger than the mixing time.
Yes. Yeah. So sorry, yeah, I should have mentioned this. So here we are assuming that the mixing time is, let's say it's a constant or something like that. But yeah, we will, like the number of samples that we'll be leaving out will be constant factor, because our buffer size is of that of tau mix. So we'll be leaving constant factor this thing. So in some sense, tau mix can depend on T, and still the rate will be the same. It's just that our buffer size will become larger and larger, which ideally we don't want. But yeah. Any other questions about the result? Yeah.
Our algorithm where you take a jump size you
Yeah.
and then you take all sheets and combine them together, that you don't know who this doesn't work. I mean, you don't know.
We don't know how to analyze that because there are so many dependencies that it becomes very hard to provide this sort of optimal analysis there. We do have some empirical evidence that does not work as well. Like there we can show that it converges, it does reduce like the error, but it plateaus out before the error achieved by this method.
Each instance itself is independent. The instances are not independent. Because there are of different tau sigma, so they are.
So you're saying that take one buffer and completely process it, or
if you show the picture.
Yeah, let me show the picture again. Yeah.
Yeah, it's not fun. You take all the green as one instance. You shift it by one. Take it as a second instance. Shift everything by one. Take it as a third instance. You combine all these instances.
So you want to take all these points as one instance, right?
Green points is one instance.
Oh, all the green points as one instance.
Green points by one. You take it as another instance.
Okay.
And so forth.
So that is what we call this parallel SGD kind of method. The issue is that that method would not be streaming, right? Because you will need to keep everything in the buffer, whereas here our buffer size scales only linearly with the mixing time. Any other questions? Yeah. Yeah. Uh, that's the problem with having these animations. Yeah.
Why isn't sigma min of G just sigma square?
Sigma min.
Like capital G matrix, what is the expectation?
The expectation is over, like, whatever is the randomness in the, like, in epsilon t. So this G has factor of A star also, right? Because you have A star into X plus epsilon, right? So when you take this expectation, you will have A into the expected value into A star. So A star into this thing plus sigma square identity. So it has a component of A star also.
But then it's always larger than sigma square. Because as you said, there is always a sigma square identity.
It is larger than sigma square. Yeah. It can be.
Oh, so it's a better bound than just root D over.
Yeah. It is better bound than like basically we want to say that if sigma goes to 0, like, we ideally want this bound to be better. Yeah. There is one more sort of minor thing which we are ignoring right now, which is that this analysis works under this assumption that operator norm of A star is strictly less than 1. This nice work by Simchovic showed that at least for offline problem, that is when you are not doing this stochastic gradient descent, when you have all the points within this thing, you can actually get rid of this assumption also. Like, so your operator norm actually might be larger than 1, but under some kind of a spectral radius assumption, you are able to make it work. We are also able to do that, but not entirely. Like, there are some more assumptions that we will need there, but I will skip that part. That's not central to this talk. Let me see how we are doing on time. We have 17 minutes. Okay, so another sort of application of the same idea that we applied was to that of Q learning with this reverse experience replay. So Q learning is a very popular technique in reinforcement learning. As I mentioned earlier, this DQ technique, which was central to AlphaGo for beating this world-class player on Go. Like the Q learning and the DQ technique was central to it, and it used actually both these components that I mentioned here, that is that of online target learning and experience replay. Right. So here what we did was we took these techniques, we modified reverse experience replay with our reverse experience replay, and we were able to show that now the resulting algorithm does provably converge to the optimal solution. And in particular, one interesting thing that we were able to show was that for linear MDPs, this reverse experience replay for Q learning converges to the optimal solution, that is to the optimal policy, which is first such result. In fact, before this, before this modification, people had shown that the standard Q learning diverges for linear MDPs. So here we were able to show that by applying this reverse experience replay, we were actually able to make this policy converge to the optimal solution. Okay. So before going into the detail of this, let me first describe the linear MDP setting itself. So in linear MDP, what happens is that we have some state action pair. The number of state action pairs might be infinite now, but we have some kind of feature vector describing the state comma action pair. That is, let's say in your board game example, you have some state of the board game and the action that you take, and you can actually represent the state comma action pair there with some feature vector. Furthermore, the transition probability, that is when you go from some state after applying some action to some next state, that transition probability can also be written as a linear function, and your reward can also be written as a linear function. So AMDP is a fairly popular way to model this state action space, especially when the state action space is really large. Now, in general, one sort of popular way of solving these MDP problems is via Bellman equation. That is, Bellman, this popular Bellman equation shows that the Q function, which is basically the maximum expected reward when you are in some state comma action pair, satisfies this equation, which naturally gives rise to this thing called Bellman iteration, which basically says that given some current policy QT, so policy you can think of as given state, I have some policy of what actions I will take in each state. So given that policy, I will do this maximization to get QT plus 1. And this maximization in the case of finite state action pair you can do through some standard dynamic programming, right? Now, in the case of linear functions, what you can show is that these Q functions or this optimal sort of reward can be parameterized by this linear function. That is, suppose we have some linear function right now which defines our current policy. Then for every such policy or such linear function, we will have an optimal solution. That is, there will be some U so that this thing is maximized, which essentially means that now my Q iteration reduces to finding a W so that this equation sort of have a fixed point. And that essentially means that for a given WT, I will just solve this supervised learning problem and I will just keep on iterating. That is, I first solve the supervised learning problem, update my W, again solve the next supervised learning problem, and so on, right? So this is essentially the algorithm that you'll get, that is starting from some policy which is represented by W0. You will solve this Bellman iteration. And now, because this Bellman iteration is a linear regression problem, we can use our stochastic gradient descent with reverse experience replay, and we will repeat until convergence. And as I mentioned earlier, prior work sort of analyzed Q-learning only for tabular setting. In linear MDPs, this simple, at least Q-learning method was known to diverge. But now with this SGD-RER, we can say that this will actually converge to the optimal solution. I will not go in the exact detail of this result, but what we can show is that Q hat, that is the policy that we obtain, will approximate the optimal policy up to this error of 1 by n. Note that there is no dependence on, again, the mixing time here. So this is again independent of the mixing time. Okay. All right. So again, ChatGPT was very happy with our progress. So it wrote this nice poem. And it is saying that, okay, let's embrace reverse experience replay with open hearts. So we thought that, okay, let's apply it in practice. And we were very sort of, bullish. We directly applied this technique to some standard, reinforcement learning domains. And what we observed was that the method was failing miserably. In general, it was not doing well at all. And we realized that the reason for that is that this mechanism of just taking each buffer and basically pivoting around it does not work. We need to do a little bit more. We need to be more careful. So the new idea that I did not come up with, but my collaborators Dheeraj and Ramnath came up with, was to pivot according to the loss function in the buffer. That is, you look at your data points, you find out a batch where the loss function is the highest, and you basically set that batch as your buffer that you process. So this is how you sort of set your pivots. And after that, you within each buffer, you are again applying reverse experience replay. And this technique magically works pretty well. So here, I'm showing 4 domains in which this Q learning with RER was applied. This is an off policy setting. And here, this RER++, which is this pivoting plus reverse experience replay, is represented by this green bar. One means that the algorithm is doing well. One is basically, it means that the relative reward of the policy or the algorithm is highest. And 0 means that the relative reward of the method is absolutely minimum. And what we observe is that this reverse experience replay ++ method performs nearly the best in each of these domains. Here I am showing only 4 domains. Dheeraj and Ramnath did these experiments in 10, 12 domains, and we observed similar thing in each of the domain. Whereas there was a bunch of other methods like this uniform experience replay and prioritized experience replay, hierarchical experience replay, and even this reverse experience replay. All these techniques in some domain they will work well, but in some other domain they will give completely garbage results. So this technique, the advantage is that it works stably and performs well across all the environments. Yeah.
What is exceeding 1?
Yeah, so as I mentioned that one, for that environment, 1 essentially means that this policy achieves, out of all these policies or out of all these algorithms, achieves the highest accuracy or highest reward, sorry.
Saying something more than 1.
Oh, that's because that's a silly reason. Basically, I was not able to show this UER of value, which had value 0. So I added value of 0.01 to everything. So this was just a hack. Yes. So this was basically due to my limited Excel skills, nothing else. Any other question about this? So yeah, like as I was saying that by applying this like sort of slight modification of reverse experience replay, this technique works pretty well, and like at least in like this off policy reinforcement learning with the DQN thing, it seems to be doing pretty well. So we are quite excited about it. Yeah. Yeah. So again, like we are not keeping the entire like buffer, but we are going to slightly larger buffer size. So like 2 or 3x the buffer size we go. And there is another experiment that these folks have which show that that does not slow you down a lot. That is, the algorithm is still practical, the training time or etc. does not increase too much. They are not correlated. So that's what I will come to in next few minutes. Yeah, I have 7 minutes, so I can try to explain what's happening here. So let's just set up the notation. Let's take the linear dynamical system as the running example, right? So first, let's understand why standard stochastic gradient descent in the independent setting works. So the independent setting is where, let's say, I am sampling xt and yt, and let's say yt is realizable. That is, yt is given by inner product of w star with xt plus some noise. All right. So here, when you write down the stochastic gradient descent, like one step of stochastic gradient descent, this is how it looks. That is wt plus 1 minus w star. You can write like this, right? And if you expand it by using the fact that yt is realizable, what we observe is that wt plus 1 minus w star is is this matrix I minus eta xt transpose times the previous iterate plus some noise, right? And you can again explain wt minus expand wt minus w star in terms of wt minus 1 minus w star, that is in terms of previous updates. And what you observe is this sort of unrolling of the equation. So here you can observe that like if you look at the expectation, this term is completely independent of epsilon t minus 1, and similarly epsilon t is independent of xt. So in expectation, this quantity is 0, and we are decreasing error, right? And so this is a geometrically decaying term. Again, because all the data points xt's are independent, what essentially you get is I minus eta times expectation of this quantity, which is some sigma. So as long as your covariance matrix sigma is strictly positive definite, you will have some kind of decrease, right, in expectation. So that says that you will converge, your expected value of w will converge to w star eventually. This is not correct proof, or like this is not a proof, because convergence of the mean of your iterate does not mean that your iterate themselves will converge, but that you can work out. I will not go in detail, but basically for that what you need to do is take the error in the iterates and write its covariance, and we will be able to show that the covariance itself is bounded. But I will ignore that for now. But now when you apply, say, stochastic gradient descent to the same thing, right? If you remember, like we had this term earlier, right? Like this is the key term that comes up. If you apply SGD to this dependent data, then this expectation doesn't go to 0, right? And that's the problem. That this, because of which SGD is biased, we cannot apply it, right? However, if you think about it, reverse experience replay is precisely solving this problem. That is, if you look at the update that is given by the reverse experience replay, it has terms of the form where x b minus t is multiplied with epsilon of b minus t plus 1. So here, like, here xt was multiplying with epsilon t minus 1. That is, previous iterates error was, or noise in the previous iterate was getting multiplied with xt, and this is not 0 mean. But here the opposite thing happens. That is, xb minus t is multiplied with epsilon b minus t plus 1, right? That is, the noise in the next iterate is or next point is multiplying with my current point's covariance. And because of that, this expectation term completely goes to 0, and we can show that will converge. Like it is in expectation, it shows that expected value of wt plus 1 converges to w star. A lot more work needs to be done because this is not enough. We will need to show that the covariance also behaves nicely. But trust me, that can be shown. I'll just ignore all this. So let me just summarize. Learning with dependent or micro-event data is quite important because reinforcement learning, time series analysis, like there are a bunch of applications here. In the worst case, like if you don't make any assumption about the Markov data, then even for linear regression problem, we will suffer a mixing time factor, which can be quite important, especially in reinforcement learning problems where every sample is really critical. So just wasting so many samples cannot work well in practice. However, when the noise has some kind of martingale increment property, then we can show that the algorithm, then we can show that at least information theoretically, we can get rid of this tau mix factor. And what we are showing is that by using reverse experience replay with some more sort of, tricks, we can show that, this tau mix factor can be completely removed and SGD works well. And we could show this works in linear dynamical system, non-linear dynamical system, as well as Q-learning. In terms of future directions, there are a lot of open directions. So first of all, I talked about this RER++ method, which works well in practice, but so far we don't know why, as in we don't really have a formal proof for it. So that's one problem that I feel is very important to understand and figure out what's happening. But then another thing is that most of our work applies to only linear regression. That is least squares problem. So applying this to more general loss functions would also be quite interesting. Okay, so thanks a lot for listening. And again, ChatGPT is quite happy and like quite excited about reverse experience replay. So that's all I have.
Questions?
Yeah. It's a good question. Right now, we don't know. So we don't know, for example, that rather than using tau mix size buffer size, if you have root tau mix, then what happens? Like, will it lead to still like 1/t or like, constant size? We don't know at all. Yeah. So that's a great question. And I'm not sure. And another thing is that this gap thing also is quite annoying. So ideally we want the buffers to be like, because in practice people use overlapping buffers. So can we use overlapping buffers and still provide some analysis? That also we don't understand. Yeah.
So in the RL application to Q-learning, do you have any dependence on the action size of the action space, or you don't know?
So those terms are there. I am hiding all those. So in linear MDP we don't, but we have dependencies on the norm of the parameters. And in the tabular setting also we have the analysis. There we have the standard dependencies. That is the state size and action size that will come in the error term. But like basically there we are matching whatever is known, like whatever is the best known there. We are able to provide analysis that matches those optimal rates.
Thank you.